I'm very glad to present you Professor Yamashita from the Department of Chemistry of Tohoku University. So Professor Yamashita is known for his research field in the crystallography, molecular magnets, stereochemistry, and magnetization, especially instead of using conventional magnet based on metallic, organometallic compound. He developed some very interesting nano single magnet and nano molecular magnet with very interesting properties. Today, Professor Yamashita will present us a talk about molecular spin qubit for quantum computer and high-density memory device. So please, Professor Yamashita.
Thank you for kind introduction. So today, I focus on the molecular spin qubit for quantum computer and high-density memory devices. So everybody knows last year Nobel Prize in Physics. So this is given to the experimental evidence of quantum entanglement. So this is a big experimental evidence. So this Nobel Prize in Physics quantum entanglement is strongly correlated to the qubit. So then quantum computer. So today my talk is first focus on the quantum computer and second high density memory devices. So first I focus on the spin qubit and the coherence at room temperature. So you know every day you use a classical bit in the personal computer PC 0 and 1, but quantum bit qubit. So this is a superposition 0 and 1. So if you use a classical bit, the calculation takes 12 days. But if you use a qubit, calculation takes 60 minutes. Huge progress. So then I focus on this qubit. So then, as I told you, minimum unit for quantum information is a superposition of 0 and 1. So then this is available for the quantum computer. So only one quantum computer is working from the IBM in USA, but followed by China and also Japan. So the low temperature is okay because first IBM quantum computer is put into the liquid helium, but more recently quantum bits available for the quantum sensor. So then to apply biological system, then room temperature is needed. For this purpose, room temperature is very important for working. So then several qubits for photons, quantum dots, and superconducting loop. This is a first one discovered by IBM and trapped atom and nitrogen vacancy in diamond. But more recently, molecular magnet become a good candidate for qubit because merit is a spin phase controlled by fast EPR, high spin polarization of electron spin, and high molecular durability. However, disadvantage or demerit is a short lifetime of superposition, spin, relaxation time. We must elongate the longer T2. So then this big disadvantage. So then this is a definition of spin relaxation time T2 and spin lattice relaxation time T1. So everyone knows this definition. Most important thing is double T1 is larger than T2. This is a very important critical condition. So then, as I told you, spin lattice relaxation time T1. So factors inverse to T1 is the inner magnetic field, such as a nuclear spin or magnetic dipole interaction. And also in the spin relaxation time T2, the factor inverse to T2 is the nuclear spin, neighboring spin, or rotation of mesh. So this is an example T2 of molecular-based magnet. So more than 100 microseconds is enough So some metal complex, vanadium complex is more than 100 microseconds. And also, vanadium ferrocyanide is room temperature. So then metal complexes, good candidate for the next generation molecular spin qubit. So then this example, square pyramidal vanadium, vanadium compound, and also octahedral sulfur coordination vanadium compound. This relaxation time. So then important thing, this terahertz optical region, you can see depending on the compound, peak is second or peak is 1. So depending on the compound, peak is split into doublet or singlet. So this is a very important information. So then we compare the other compound, vanadium compound 1 and compound 2, vanadium compound. You can see compound 1 has a 2 relaxation time. Compound 2 is a 1 relaxation time. 2 relaxation time compound shows a doublet peak, and 1 relaxation time has a single peak in the terahertz region. We observe the relationship between magnetic and optical property. This is very important. So then, as I told you, most investigated compound is vanadium. This speed is 1/2, and also coordinate vanadium also speed 1/2. So one spin system is very good candidate for molecular spin qubit. Other example is the chromium 5 or cobalt 2 plus low spin, copper 2 or nickel 3 low spin or iron 3 low spin. All have a spin is 1/2. So this is not single mode magnet. This is a molecular-based magnet. I focus on all these one spin system. So then today I first focus on the crystal engineering method, so-called metal organic frame MOF spin qubit. So this means the suppression of intra and the intermolecular vibration of TPP by using 3D MOF. So then, you know, the copper energy in the crystal planar structure. However, in the vacuum condition, distorted structure. So this means that crystal lattice will suppress the intramolecular vibration. Crystal lattice is very important. Then I focus on the TPP vanadium. So in the zero dimension, lattice is very soft, but put into the MOF, metal organic framework, 3-dimensional MOF. So lattice is very rigid. We compare the soft lattice, zero dimensional, and the 3-dimensional MOF to make clear the factors of the spin behavior induced by the crystal lattice. So then we synthesize the tetracarboxylate benzyl TPP vanadium, zero dimensional, put zinc to make a 2-dimensional, put the bipyridine to make a 3-dimensional MOF. I compare the zero dimensional starting material and the 3-dimensional MOF for T1 and T2. So then this is a crystal structure. This is a zero dimensional starting material, and this is a 3-dimensional MOF. So metal-metal distances are a little different. So this EPR spectrum diluted in the titanium oxide, non-magnetic titanium oxide, 3-dimensional MOF, zero-dimensional starting material. You can see G perpendicular parallel by EPR. Same value. Same value means that 3-dimensional MOF and zero-dimensional starting material has the same electron structure. So then we compare the terahertz. As I told you, we discover the correlation between optical properties and magnetic property. So zero-dimensional compound shows a strong peak around 67 millimeters. This is the deformation of the molecule and also stretching more. And like this theoretical calculation, deformation of the molecule. And but 3-dimensional MOF, no peak, because we suppress the lower energy of the deformation of the 3D MOF, because 3D MOF is very strong lattice, then no peak in the terahertz region. So then this is a result. So this is 3D MOF. So you can see even at room temperature, we observe the quantum coherence even at room temperature. And also, we measure the Rabi nutation. Rabi nutation usually pulsar detects the echo. Usually, Rabi nutation observes a very low temperature, 4.5 Kelvin. But my compound, 3-dimensional more, even at room temperature, very beautiful Rabi nutation is observed. So then, in the case of 3D more complex, Rabi nutation or coherence was observed due to the rigid lattice even at room temperature. So then, next target, the kappa. Usually, bulk kappa complex shows the antiferromagnetic interaction. However, if kappa molecule doped into the diamagnetic 1-dimensional, 2-dimensional, or 3-dimensional more, so diluted, then we detect the only one kappa ion. This should show the slow magnetic relaxation and should show the spin qubit. So then I focus on the non-magnetic platinum-2 mixed balance compound. This chemical formula. So platinum-2 mixed balance compound, counter anion perchlorate. This is a 1-dimensional lattice. Counter anion halogen. This is a 2-dimensional lattice. So we compare the 1-dimensional and 2-dimensional lattice. So then we dope the kappa, 5% kappa dope. So we detect the slow magnetic relaxation of the 1-dimensional perchlorate. This is due to the 1 kappa ion. And also 2-dimensional slow magnetic relaxation due to the kappa ion. So kappa ion shows a slow magnetic relaxation. Then 2-dimensional compound is longer coherence time larger than 1-dimensional compound. 2-dimensional is better. So then we next use the MOF, metal organic framework. So you know zinc MOF. This is a diamagnetic species. We dope the kappa into the zinc MOF, 3-dimensional MOF. So then slow magnetic relaxation observed. This is evidence of spin qubit, slow magnetic relaxation. So from the Allen's plot, so this is due to the phonon bottleneck effect. This is not single multi-magnet, but the phonon bottleneck effect. So then next pressure blue halo. So hexacyano-cobalt is a diamagnet. We put the iron hexacyano complex. This is a 1 ampere electron. So S equal 1/2. So I doped this. This is a crystal structure of cobalt. So then you can see slow magnetic relaxation observed due to the 1 iron atom. Iron atom has a 1 spin. So slow magnetic relaxation. So then from the Allen's plot, low temperature, phonon bottleneck effect, and the high temperature Raman process. So let's move to the g-Tensor engineering method, relationship between isotropy of G values and T1 in oxyvanadium TPP and chromium nitride TPP. So you can see, originally g-Tensor engineering reported by Professor Wing Penny in Manchester. So multi-bit system by using isotropy of G values and special arrangement. But we usually use the electron spin will be influenced by the vibration if G values have highly isotropy. So we compare the oxyvanadium spin 1 spin system, chromium nitride 1 spin system, same electron structure to make clear the influence of isotropy of G values to T1. So this is a crystal structure. So chromium or vanadium are distorted from the square planar. So then this is the EPR spectra, chromium nitride, oxyvanadium diluted by the titanium oxide. So this is isotropy of G values. So chromium nitride has a 0.0398. Oxyvanadium has a 0.0235. Chromium nitride is larger isotropy. So then, so this is a result. Chromium nitride is faster relaxation time, but oxyvanadium is longer lifetime. So oxyvanadium longer lifetime because smaller isotropy of G values. So then both compounds show slow magnetic relaxation. These are actually molecular spin qubit. And then oxyvanadium better than chromium nitride due to the isotropy of G values. This is so-called g-Tensor engineering method. Third one is the orbital engineering method, relationship between different occupied orbital Nix-3 complex. Nix-3 complex is usually very unstable, but we stabilize by macrocycle ligand. So actual ligand is the NO3 and the counter NO3. This is abbreviated nickel NO3. And the actual ligand is chloride and the counter perchlorate. This is abbreviated nickel chloride. So then bulk nickel chloride shows an anti-ferromagnetic interaction. Then we diluted the cobalt complex, cobalt-3 complex. Cobalt-3 is diamagnetic. So nickel-3 is diluted. We detect one nickel-3 ion. So this is the EPR spectrum. So this square orbital is occupied in one spin. So both compounds show the slow magnetic relaxation. This is evidence of spin qubit. So this is a result. Nickel NO3 is a red one. Blue one is nickel chloride. Nickel NO3 is a longer lifetime because oxygen coordinate. Oxygen has no nuclear speed, but the chloride has a nuclear speed. Then nickel chloride is a faster relaxation time. So then, and also nickel MLT. This is a planar structure, but this you can see diamagnetic, paramagnetic, antiferromagnetic interaction. Then we dope nickel compound into the diamagnetic gold compound. So then you can see ampere electron is a d square orbital, different orbital of the octahedron. So then slow magnetic relaxation observed. This is a candidate of molecular spin qubit. So then these are all results. Nickel MNT is the shortest because this molecule stretch mode is very strong. However, macrocycle is a rigid. So then nickel chloride, nickel NO3. Nickel NO3 is the longest lifetime. So in these nickel-3 compounds. So finally, I focus on the molecular technology method. Molecular technology is perfectly different to the molecular design. Molecular design to realize a property, but the molecular technology to realize a real application. So relationship of T1 spin lattice relaxation time between VO TPP and VO aniline new macrocycle ligand. So this result of the already reported compound 1, longest lifetime, compound 2 here, and oxyvanadium TPP and phthalocyanine here. But we focus on the different macrocycle, propyl, aniline macrocycle, and hexyl, rigid, aniline, oxyvanadium, propyl, and hexyl to make clear the influence of ligand symmetry of T1. So this is a crystal structure. So then propyl is disorder, but the hexyl is rigid, and this a little bendy. So this is a crystal structure, metal-metal distance is described. So this is the EPR spectrum. As I told you, propyl is disorder, so then very complicated EPR. However, hexyl is very clear. So then we simulate. Hexyl is 0.0207. Oxyvanadium 0.025. So then hexyl is smaller isotopic. Then result you can see. So this oxyvanadium TPP, this is hexyl. Hexyl is longer lifetime because smaller isotopic. Surprisingly, propyl is the longest all compounds. So and you can see both compounds show slow magnetic relaxation. Both are candidate of molecular spin qubit. So these are result. So all vanadium compound propyl is the longest, but I don't know the reason. So then we need the molecular technology by using the theory. So then we must realize the molecular spin qubit at room temperature and also longer T1 and T2 long coherence time. That is our final target to realize the quantum computer based on the molecular spin qubit. So let's move to the high density memory devices. So first one is single molecule memory performance by single molecule magnet. Second one is a metal covalent single molecule magnet encapsulated into the single carbon nanotube, and metallic conductor single molecule magnet with negative marginal resistance, and the photo switchable single molecule magnet. Every day you use the classical magnet, but every day I use a single molecule magnet. Why? Why should we use single molecule magnet? instead of classical magnet. So answer to overcome the Moore's limitation. So human being face the Moore's limitation. We must overcome the Moore's limitation. So what is Moore's law? So unfortunately, Moore passed away 2 months ago. So Moore's law, every 1.5 years, memory capacity increased twice according to the Moore's law. So now 2023 here. So to increase the memory devices, we must make the classical magnet smaller into nano size. However, classical magnet does not work in the nano size, just quantum fluctuation. Then we must use the nano size magnet, like the magnet to overcome this. Use a single molecule magnet to overcome the Moore's limitation. So then, what is single molecule magnet? Everyone knows, but briefly introduce. Classical magnet, 3-dimensional ferro or ferrite magnet ordering, but single molecule magnet is a 0-dimensional and made of the mono or multinuclear nanocluster metal complexes. So no intermolecular interaction independently exists. However, this molecule has a double potential. Below working temperature, upstream or downstream frozen, and magnet. So one single molecule magnet works as one magnet and works as one memory. We use this single molecule magnet. So this is another view. So below working temperature, upstream or downstream freeze, and this is thermal relaxation, and the quantum noise is the same. So quantum tunneling occurs. So then you can see this thermal relaxation as a hysteresis, and you can see the step. This is quantum tunneling. So this is available for the memory devices and the quantum computer, and also frequency dependency in AC susceptibility. In the classical magnet, antiferromagnet, classical magnet, we switch from 1 Hz to 1000 Hz. No frequency dependency in the bulk magnet, 3-dimensional classical magnet. However, in the single molecule magnet, very beautiful frequency dependency, so perfectly different. So then heat capacity is very powerful method to check the ordering. So then in the antiferromagnet 3-dimensional ordering, at the needle point, very sharp peaks observed in the heat capacity. This is evidence of 3-dimensional ordering. However, in the single molecule magnet, no intermolecular interaction, 0-dimensional, no ordering, no peak, perfectly different from the classical magnet and single molecule magnet. Then single molecule magnet, so-called 21st century new magnet. So then to overcome the Moore's law, we must make the we must use a single molecule magnet to overcome the Moore's law. So then our final target is in Japan National Library, 20 million units. All information are stored in the sugar cubic size memory device. This is our final approach. So another interesting point is spintronics. Last century, electron is a technology. Electron is based on the freedom of charge of the electron, but spintronics is based on the freedom of charge and spin of the electron. So then spintronics has much advantage compared to the electronics. So then for the magnetic random access memory, MRAM, advantage of the spintronics is no volatility of information, high operation speed of nanosecond, high information density, low consuming electric power. This is a bigger advantage of the spintronics compared with the electronics. So here is some spintronics such as the magnetic resistance. First one is the giant magnetic resistance, GMR, and the tandem magnetic resistance, TMR. Every day you use the GMR, TMR, your own personal computer, your PC, and CMR, DMR, EMR, all magnetic resistance. Then let me show the example, giant magnetic resistance effect. 1988, Professor Gurenberg discovered GMR. They got the Nobel Prize 2007. So this is a classical magnet, non-magnet, and classical magnet. Spin is anti-parallel, so low conductors, definition 0. Spin is parallel, high conductors, definition 1. 0, 1, 0, 1 switching in the classical magnet. However, this is a classical magnet. To overcome the Moore's limitation, we must use a nanomagnet, such as a single molecule magnet. We must use every time. We must use a single molecule magnet to overcome the nuance limitation. For this purpose, we usually use a scanning tunneling microscopy (STM). It's an instrument for imaging surface at the atomic level, and also we usually use a scanning tunnel spectroscopy. This provides information about the density of state. So the tunnel conductance DIDV is directly proportional to the sample dose. We usually use this STM and STS. So this is a condition of STM and STS. So the first topic is the single molecule memory performance by single molecule magnet. We put the information into the single molecule magnet upstream, downstream, 0, 1, 0, 1 into single molecule magnet. So then in this case, we use a tunneling monoton resistance TMR. So in the hardest case, spins parallel, high conductance on the disk definition 1. Spins antiparallel, low conductance division 0, 1, 0, 1, 0, switch. However, this is a classical magnet. We use a single molecule magnet instead of a classical magnet to overcome the Moore's limitation. So how to write and read one memory in single molecule magnet? So in this case, chip is a STM chip is a electrode 1. So sample is a single molecule magnet. This is electrode 2. So we use this electrode 1 and electrode 2 instead of classical magnet. We use a single molecule magnet. So spin of the chip and the spin of the single molecule magnet is parallel in the tunnel mounted resistance, high conductance. So division 1. Spin of the chips and the spin of the single molecule magnets anti-parallel. So low conductance, division 0, 1, 0, 1, 0 switching. So by using the single molecule magnet, so to realize a single molecule memory devices. So, but you must believe now spin is up or spin down. Now 0 or 1. So then we must visualize magnetization by TMR. So chip of the spin down and the spin of the single molecule down, dark color, and up, bright color, dark color, or 0, 1, 0. Dark color is spin down, bright color spin up. So you can distinguish now spins down, spins up by color change. And also we use a preparation of the chips for spin polarization. So bulk cobalt is a ferromagnet, but one cobalt atom paramagnet. We usually use a chip of the platinum iridium chip. So we put to the bulk cobalt, then take one cobalt atom. One cobalt atom is a paramagnet. We use a platinum iridium one cobalt atom. So this is a result. This is a classical magnet. So this is a cobalt bulk. Cobalt bulk is a classical magnet. You can see spin of the chip is down. You can see bright color. Spins up, yeah. Dark color, spin down. So 1, 1, 1, 0, and bright color, dark color. Like also again, black, white, down spin, up spin, down spin, up spin. So then we move, show the movie. So we see the external field. Okay. Spin flip. So color change. Now spin down. Dark color. Spin down. Spin down. Spin up. Spin up. He puts a information 0, 1 in the classical magnet. Color change. You can believe now spins up, spin down by color change. So this is a unfortunate classical magnet, bulk magnet. Okay. So then in this case, we show the spin down, 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 up, like this. And up, down, down, down. Large pieces observed. So then we must realize single molecule magnet. So this is a single molecule magnet. We access to one molecule. We put the information upspin or downspin in the single molecule magnet. Okay. So this is a single molecule magnet. Okay, dark color. Now spins down. Spins down. Okay. So then I see like here. Yeah. Now 1.0. Now spin up, bright color. Now spin up. Now spin down. We put the information, one spin, into the one molecule. Okay? So now spin down. Dark color, dark color. Now 0, 0. Color change, spin up, 1. Now 0. So we realize single memory device by using the single magnet. So then, unfortunately, this is Japanese. So by making the monolayer, we use a multi-spin system and we seek the information, we seek these information. So let's move to the metal fluorine single magnet encapsulated single carbon nanotube showing giant amount of resistance. We must use every time single magnet to overcome the Moore's mutation. So then single magnet, single carbon nanotube is a mixture of the 80% metal, 80% semiconductor and 20% metal. So we insert the single magnet. So conduction electron and local single magnet interact to show the negative magnetic resistance. It's a new spintronics. So we inserted the dysprosium-1 or terbium double capital sign single magnet into single carbon nanotube. So like a keyboard. So this is a motif. So this is a synthetic metal, very high vacuum condition and high temperature. So in 2 days and wash outside. So this is a result. This is a table image. You can see this is a motif. So metal fluorine single magnet inserted, encapsulated into single carbon nanotube. And this is EDX, dysprosium and scandium is already observed. So this Raman spectroscopy, this is very sensitive for the charge transfer. So before, after encapsulation, red shift observed. So this means the charge transfer from metal fluorine to single carbon nanotube. Interaction occurs in the between single carbon nanotube and the metal fluorine. So in this point is the coercivity. Before encapsulation, coercivity 0.5. After encapsulation, 4 QRS. 1 order increase after encapsulation. So this means that quantum tunneling suppressed. So other single magnet is the terbium double capital signing. This compound. In this case, I use a solution method and wash outside. So this is the result. You can see double capital sign inserted in by term image and EDX terbium is included. So I'm sorry, this is Japanese, but I take 1 carbon nanotube by lithography, put electron to measure the magnetic resistance. So first, I use a gold electrode, but this is a single carbon nanotube. Okay, so this is the electrode. No magnetic resistance, no resistance. However, we switch from gold to nickel. You can see magnetic resistance observed 0.37, very small, but the magnetic resistance observed in the nickel. So this is the first example of the magnetic resistance. Conduction electron and encapsulated single magnet interact to show the negative magnetic resistance. So let's move to the Coulomb blockade oscillation. So this is a palladium electrode and electron beam lithography. We take this 1 carbon nanotube. You can see 1 carbon nanotube. So this is a double capital sign inserted. So before encapsulation, after encapsulation, we check the Coulomb blockade. Coulomb blockade is a quantum tunneling. Okay. So everybody knows single carbon nanotube shows the Coulomb blockade. But after encapsulation, what's happened? So before encapsulation, in this carbon nanotube, very beautiful oscillation of the Coulomb blockade. 0 Tesla, -2 Tesla, 2 Tesla, no change because no spin. But after encapsulation, you can see very noisy, noisy. This is a conduction electron and the spin flip interact. And after 2 Tesla, red color change the blue. So magnetic effect is observed. This is a interaction between single carbon nanotube and the localized single molecule magnet. So let's move to the metallic conducting single molecule magnet with negative magnetic resistance. Every time I use a single molecule magnet to overcome the Moore's limitation, and we realize the giant magnetic resistance. So for this purpose, we usually use an organic donor and single molecule magnet by conduction electron and the localized single molecule magnet interact d pi f interaction to show the giant magnetic resistance to overcome the Moore's limitation. So in this case, we use a bedo. This is an organic donor and cobalt single molecule magnet. By electrochemically, we obtain the zinc crystal. This is a beta double prime BO3 cobalt so-called BO3. And this is a beta double prime. So this kind of organic donor stacking. So this bedo stacking and the single molecule magnet alternatively stacking two-dimensional bifunctional material. So this Raman spectra charge transfer 0.77. So partial charge transfer occurs from the donor to acceptor. So then this is evidence of high conductivity. So this shows that he says actually it's a single molecule magnet, and also frequency dependence is observed. Actually, this is a single molecule magnet, and also you can see this is electrical conductivity. This is the first example of metallic conductivity, and with increased pressure. So conductivity increases 1,000 G. So, but metal usage transition occurs around 7 Kelvin. However, this shows a negative magnetic resistance by the conduction electron and local single magnet. This is another example of negative magnetic resistance by a conduction electron and local single magnet. And from the band calculation, Kelvin level cutting. So this is evidence of the metallic behavior of this BO3 compound. Finally, we must realize giant magnetic resistance. Then we use a spin valve method, cobalt substrate. We evaporate one double decryptosine tellurium and chromium chips. So we measure the DIDB as 0 Tesla, DIDB 5, and 1 Tesla, DIDB 10, twice. This means that we realize giant magnetic resistance 200%. So we can overcome the Moore's limitation. We realize giant magnetic resistance by spin valve method. Finally. So let's move to the photo switchable single molecule magnet. So then organic DT compound, this is a carboxylase, this is carboxylase, this is a pi conjugate, this carboxylase interact. But visible irradiation, cut off, no interaction. So then photo switchable, visible UV irradiation, and no interaction single molecule magnet. Interaction classical magnet. So by UV visible irradiation, single molecule magnet, classical magnet switchable. So then no pi conjugation, open type, colorless, by UV irradiation, conjugated, colored, colorless, more than 1,000 times switchable by UV visible irradiation. For this purpose, we use a DT ligand and also single molecule magnet, manganese. So this is a crystal structure. So then this single molecule magnet is connected by pi coordination. This is a classical magnet. By visible irradiation, this carbon-carbon bond is destroyed. Then this is isolated. This is a single molecule magnet. Classical magnet, single molecule magnet, reversibly switchable by single crystal. So this is a UV visible spectra. Black one is a closed type, and the red one is a visible irradiation open type, and again UV irradiation designed to the black one. So reversibly switchable. So then open type, for the same circle. This is evidence of single molecule magnet. So this tidal pan in the AC satellite, open type, single molecule magnet, then AC is observed. And UV irradiation, closed type, classical magnet, no AC satellite. But visible irradiation again, let this observe. So reversibly, AC observe, no, not observe, observe, not observe. UV visible radiation reversibly switchable between single molecule magnet and classical magnet. So second part, I focus on the high density memory devices. So then every time we use a single molecule magnet to overcome the Moore's limitation. So then most important thing is how to increase the hysterical temperature to increase the energy gaps between the ground state and the first sublevel. Otherwise, to suppress the quantum tunneling mechanism QTM in the ground state. So as I told you, if the potential barrier very high, but at the ground state, quantum tunneling occurs, hysterical temperature is very low, then we must suppress the quantum tunneling at the ground state. So then for the double deck sign, so two important things, ideal square anti-field sub, and also exchange bias for the ground state. So this means that upper star sign, lower star sign, not distorted. Then square pair prism, G4A. So ligand field include the B44 and B64. B44 and B64 is exact source of quantum tunneling mechanism. But upper star sign, lower star sign distorted 45 degrees. D4D. In this case, B44 and B64 is disappear. So this suppresses the quantum tunneling. And also in the diamond, you can see at the 0 Tesla, no step. This means that in the diamond, at the ground state, quantum tunneling suppressed. So then diamond, two spin down, at the same time, two spin up at the ground state. This is very low possibility. So then diamond is very important to suppress the quantum tunneling at the ground state. So this is so-called exchange bias. We use this method. So then double deck sign is breathed by the benzene. Diamond. This shows he says around 25 Kelvin because starting material is less than 4 Kelvin, but the diamond is 25 Kelvin. And fuse another fuse type, hysterical temperature increased 27 Kelvin. And finally, liquid crystal 31 Kelvin. So by using the exchange bias, hysterical temperature increased. But now highest temperature is 80 Kelvin, liquid nitrogen temperature. We must realize room temperature. Okay. So, and 3 years ago, I got a Japan Chemical Society Award. So that's the highest award in Japan Society of Chemistry. So this award account, please check this award account. So from my master course student to now, you can see my research history from this review article award account. So finally, I stress, what is science? This is the most important thing. What is science? So everybody knows to create new concepts, of course. For example, new compound, new physical properties, new reactions, new theories, new measurements. Everybody does every day, but it is not science. Most important for science is to create new research field. It takes 30, 40 years. For the student, you have only one chance for your life. I started when I was a master course student. My professor, very bad, no project for me. I'm 25 years old. By myself, I must look for my own project. I started this project more than 40 years ago. So it takes 40 years. So then, to create new research field is very important. So my field is the multifunctional nanoscience of advanced metal complex. So bifunctionality, magnetism, optics, conductivity, conducting magnetism. But everybody does these fields, but this is a bulk level. I focus on the nanoscience level and metal complex. So nanoscience means that, as I told you, quantum effect and non-linearity. Today I talk about the quantum physics. But the other topic is non-linearity. So this is my field. It takes 40 years to realize this is a field. So science should be not number one, but only one. If the number one is overcome as a researcher, number one becomes number two, number three, number 10. Nobody remembers number 10. But if you forget only one, you can check the textbook. You can find only one in the textbook. So science should be only one. So science should be not from 1 to 100, but from nothing to 1. So just 1 to 100 is just development of as a researcher's work. No science. From nothing to 1. This is actually to create a new research field. So, but the importance for science is originality or creativity. And most important thing is to enjoy science. To enjoy science. This is the most important thing. So, this is natural science. Already cleared field is only 5 to 10%. Other 90 to 95% unclear. But most researchers work on already cleared field. Very boring. You must challenge. You must challenge the unclear field, but it takes 40 or 50 years. So for your only one life, you have only one chance. So as I told you, what is science? To create a research field, it will take 30, 40 years. Only one chance for your only one your life. Okay. In Japan, so people survive alive around 90 years old, average, similar to Turkey. Okay. But every day you sleep 8 hours. Every day is 24 hours, and you sleep 8 hours. That means 1/3 you are sleeping. That means in the whole life, 90 years, 30 years, for 30 years you are sleeping. Too much. 3 years enough for sleeping. Once a week, you must sleep. When I was a student, every 2 nights, just 1 hour, 2 hours sleeping, every 2 nights. Because no project, no progress. By myself, I must look for my own project. So you must realize to create your own research field. So finally, I accomplished my main coworker. This international collaboration with a theoretical or robotics solid and many co-workers. So I've already retired, but about 10 years ago, my group is more than 55 members. So very international. He's from China, India, Egypt, Bangladesh, China, France, and Bangladesh. So more than 55 members, but unfortunately, I don't remember the name of my students. Thank you for kind attention. Thank you. Any question or comment?
Did you give projects to your students?
Sorry.
Did you give projects to your students?
Every time I say, I give you for getting a PhD, but you must find one project by yourself. Okay. First topic was a 3D mold Oxford project. My student find out by himself. He didn't say to synthesize that compound. And he was a second year of the PhD course. He brings to me the compound. And he explained to me, so this 3D mold technology manager already invested, but no report was generated. So then I sent an email to all the world, which are located in Manchester or Rochester in Italy. So Rochester accept to make that passing here for method and published in journals. That project is my student own project. So then, usually students have 2 or 3 projects. One is from me, because to get a bit, but other 1 or 2 by themselves. That's very important. Yeah.
You showed some photo-switchable
Yeah.
single molecular magnets.
Yeah.
So could you suggest any energy gap between the open form and closed form? So is there any ideal energy gap between the 2 forms?
That's a good question, but maybe you check the review article. So in the review article, depending on the condition, okay, in the solid state, so photochromism takes longer time, a few hours in the solid state, okay, and the solution quickly change, quickly, depending on the condition. So.
But mostly we measure in solution.
Yeah, but in my project, solid state, so then it takes time. I show the thin crystal. So once I measure in the closed type, and after that, 1 day irradiation, and after 1 day we determine the structure and open type. So it takes one day.
It's a really nice work for me. And I have a question about the quantum computing application of the single molecule. But you didn't mention about the environment isolation. Just the isolation of the single molecule from the environment. I think how to implement, how to develop the device. For using the single molecule.
Good question. So as I told you, the only one quantum computer working by using the superconducting loops. In that case, like a semiconductor make a circuit by using the superconducting loops. So in our case, molecular spin computing, we usually use a percipient. Okay, percipient gets a spin information T1, T2, and also in STM. STM EPR conjugation access to one molecule. We obtained the signal from this year. I published in Nano Letter.
In this case, what's the superposition?
Yeah, by using the STM, we can access to one molecule.
1, 0, 1.
Yeah.
Only 1, 0. We can just detect.
Yes.
And, is it possible to use like the quantum computer?
Yeah. As I told you, so the classical computer, that's a combination of 0 and 0. But the quantum bit means a superposition 0, 1. As I told you, T1 means that this kind of behavior. And this means the superposition, not 0, 1, 0, 0, 1, 0, 1. This is a classical. But in the quantum bit, so time dependent on reaction T1 and T2. These during this time we finish the calculation.
T1 and T2, they are affected by the environment, the other field also.
Yeah.
The presence of the other field.
Yeah. Good question. Yeah, T1, T2, as I told you, very sensitive to the nuclear spin or other neighboring spin or something. So then, in my case, I doped into the diamagnetic species. So then isolated. That's very important. Because the spin interaction does make the short lifetime of T1. But isolated, no interaction, so longer. And our compound shows the room temperature for heat.
I have a short question. I'm sorry for this question. And for this spectroscopic application of molecular method and use the STM and use the cobalt atoms. Parameters. Yes. Are you using the single polarized current?
Yeah. And as I told you, bulk cobalt is a paramount, but one cobalt atom is paramount. So another candidate for one spin is enough. For example, in our case, we use a cobalt one atom. So paramagnet is very important because depending on the extramagnetic field, spin field, then cobalt is paramagnet. That's very convenient. But there are many candidates for the advanced process.
I can
Yeah.
ask. Thank you for the interesting thoughts. You emphasize that we need to go to room temperature
Yeah.
materials, but the highest one is like 80 Kelvin.
Yes.
So how much this can be improved?
Yeah.
Like, is it even possible to reach to room temperature?
I'm an optimist. Then I have to
We
realize.
need to be realistic too.
Yeah, and I thought in our case, double decoupler sign case, important thing, two things. So last one is ground state, first sublet, this energy barrier very large, okay, because it's being filled with high energy barrier. And but if the high energy barrier at the ground state quantum tunnel occurs, state temperature very low. We must suppress the quantum tunnel. Only thermal relaxation. If so, we must make the larger energy gap. But if at the ground state, spin flip quantum tunnel occurs, state temperature very low. Then we must suppress the quantum tunnel at the ground state or first sublevel, second sublevel. We suppress the quantum tunnel. If so, we realize we need to. I'm an optimist.
Question. So you show some result with terbium statocyanide.
Yes.
So, and as I remember, you terbium statocyanide have alkoxy group of substituents.
Yeah.
Why do you choose this substituent? Or do you try other substituents? And there is substituent have effect on magnetic properties?
Yeah, and usually for the lanthanide, dispersion is best. But depending on the ligand field, the double decoupler sign in ligand field.
Yes, it's
And-
moving.
Yeah, and
But this don't-
terbium is best because from the NMR analysis, we obtain the parameter of the ground state, first sublevel, second sublevel. So in dispersion case, usually best, but double decoupler sign, the first ground state, first sublevel, only 20 wave number far away, but in the terbium case, more than 400 wave number far away. So then terbium is better.
I'm wondering the suppression of the formation. When you got move and suppress magnitude, right? Not suppress frequency. Molecular formation frequency always
And as I told you, in the zero-dimensional starting material shows a very sharp peak in the terahertz 67 wave number. And the three-dimensional no peak. If we measure the higher, we observe the peak. But I don't check. That's a good idea, but nobody done. Nobody done. So there's measurement not so popular.
Yes.
Equipment is also not popular. in Japan, I was looking for my coworker to measure the terahertz.
Just go to scuba.
Yeah.
So you know the Kadawaki group.
Yeah. Not so many, so not so easy to measure the terahertz.
So no more question? So Professor Yamashita, please for your talk.
Thank you very much.
Thank you.